Hello everyone and welcome back. Today we're going to be discussing one of the last few static situations involving fluids, and that is known as Pascal's Principle. To get the point across as to what this is, I'm going to use this empty soda bottle here. So this is a typical plastic 2-liter soda bottle, and it is capped, which means it is completely sealed and there's no connection to the outside air pressure. Now if this bottle was empty and I capped it, that means the air pressure outside is atmospheric, and the air pressure inside is also atmospheric because I haven't done anything to the bottle yet. Now, I want you to imagine here that you grab this bottle and you push your finger into the bottle so you dent it. In other words, you squeeze the bottle in this one section so you actually indent the bottle. Well, that means that there is now less volume in the bottle. And as long as the bottle is capped, and you decrease the volume, there is going to be an increase in pressure inside the bottle. Now, what Pascal's principle states is that even though you only push in this area, the pressure increases inside the bottle everywhere. In other words, what you do to one section affects the whole thing. The same thing holds true if this is filled with a fluid. Let's say this whole fluid here. Well, at this location down here, if you wanted to get the absolute pressure here, you would need the pressure inside this area up here, I'll just call it Px, plus pressure at depth, rho g h. If you indent the bottle here, then the pressure Px is going to increase because there's less volume in this upper area. Well, if that holds true, then the pressure at depth also has to increase because it is also reliant on Px. So the statement I just gave, that if you increase the pressure in one area, then that pressure increase is applied to the entire volume, as long as that volume is contained. In other words, there's no open area to the atmosphere. Another way to state this mathematically is, if I increase the pressure in one area, let's say this part right here where I'm pushing in with my finger, then the pressure at any other area in this volume is going to increase by the same amount. Let's say this area all the way down here at the bottom. So again, what you do to one part of this will affect the entire closed system. So I'm going to show you the single most common type of problem you will see regarding this. What you see on the screen here is a very simple hydraulic lift. I have a pipe here, which is thin, and a pipe here, which is thick, and they are both sealed with pistons. So A is a thin pipe and B is a thick pipe. Now, if I push down on this piston will go upward, and vice versa. But if you notice, this one has much less area than this one. So let's see how this relates to Pascal's principle. For simplicity's sake, I'm going to make up some pretty easy numbers here. I'm going to say area 1 is 0.5 meters squared, and area 2 is 8 meters squared. And I'm also going to add something else to the problem, which is going to be a vehicle. So there is literally a car on this hydraulic lift. Now, if I asked you, could you lift this car into the air? The answer, if you were using nothing but your own body, would probably be a no. However, using this system, you can, and I'm going to prove it to you. Let's say the mass of this car is 2,000 kilograms. That means force Earth on car is mg. 2,000 kilograms times 9.8 newtons per kilogram. We're going to be 19600 newtons. And that is what is pushing down on this piston into the fluid. You, however, are at this piston, and you are pushing down on this piston with the goal of lifting this car up into the air. So first, let's find out how much force you would need just to keep the car from not moving at all. Well, to do that, we're going to find out how much force you need to exert due to this area. Because remember, the force exerted over an area in one part of the system transfers to the entire enclosed system. I'm going to move this here so we have some space. I'm going to call this force 1, and the force the weight of the car exerts force 2. We're looking for force 1, so I'm going to multiply area 1 on both sides. Force 2 times area 1 over area 2, 19600 newtons, 0.5 meters squared over 8 meters squared. Meter squared cancels, and I get 1225 newtons. So exerting a force of a little over 1,000 newtons, you can keep this car stationary, which is almost 20,000 newtons. And that is because the force you exert over this small area here is then distributed to the force of this larger area on this other piston. So if we took a look at the mechanical advantage of this tool, it'd be force out over the force you put in. 19600 newtons over 1225 newtons, which would be a 16 times force advantage. So a little side note. Notice this also matches the division of the areas. 8 meters squared over 0.5 meters squared also gives me 16 times. So two things here. One of them, if you are asked how much force would it take to lift this car, this is the answer. And you may say, but Mr. M, this keeps everything even, which means the car isn't going anywhere. Well, that's true. However, it is also true that if you exert a hair more than this force, let's say 1226 newtons, that means the force you exert on the fluid would increase. That force would be distributed throughout the entire liquid, which includes this piston. So the force on this piston upward would increase. Force earth from the car does not change. So if you exert even a slightly larger force, it would begin to accelerate upward. Once it is moving upward, to keep it at constant velocity, all you need is a net force of 0, which means back to 1225 newtons and 19600 newtons. In other words, once you got it moving, all you would need is to maintain this force to keep it moving upward. So yes, you can lift a car using much less force than the actual weight of the car is. The actual advantage you have in this situation is a 16 times advantage based on the area of the pipes, which I just made up. So now that I've said that, let's talk about the disadvantage of this situation. All right, so I'm going to move some things around here so we have some space, and I'm going to ask a question. And that question is going to be, if you push this piston down, which I'll call height 1, how much does this piston rise, which I'll call height 2? In other words, the whole point of this problem is to lift the car. Well, how much would the car actually be lifted? And we're going to take a look at this two ways. First, we're going to take a look at it in terms of actual volume displaced. In other words, if you push this piston down, you are displacing this much volume of fluid, which means that much volume of fluid must be added to the other side. Since this tube is not very wide, you're pushing down a certain amount. This tube is wide, it's not going to go up as much. The volume you displace here has to be the same amount of volume you displace here, because we're not gaining or losing any fluid. So I'm going to call this left area 1 still. I'm going to say volume 1 equals volume 2. The amount of fluid you're moving this side has to be added to this side. Well, it's a cylinder, so volume 1 is going to be height 1 times area 1, and volume 2 is height 2 times area 2. For simplicity's sake, let's say you push the piston down 1 meter. So height 1 is 1 meter, area is half a meter squared, equals height 2 times 8 meters squared. If I do this, these 2 meters squared cancel, and I get a height 2 of 0.0625 meters, or 6.25 centimeters. Now we're going to do this again, only this time we're going to do it in terms of work, of energy transferred. So if you are pushing down the piston, you are doing work, because you're exerting a force over a displacement. This is a transfer of energy, so where is the energy going? Well, you are lifting the car up into the air, so the energy is going to gravitational. Work is force power law that you are pushing times the displacement, and the car is gaining gravitational, which is mgh. We have the forces exerted here on the lower left, 1225 newtons. We said you push it 1 meter. Now mg is the weight of the car, which we have right here, 19600 newtons times height 2. I divide out the weight of the car, newtons cancel, and again, I get a height 2 of 0.0625 meters. So I can find how high the car is lifted based on the volume displaced or how much energy was transferred. Because on this side, the fluid is conserved. You don't lose any, you don't gain any. And on this side, energy is conserved. The amount of energy you put into the system equals the amount of gravitational potential energy gained. So Pascal's principle basically states that if you increase pressure anywhere inside a closed system, then that pressure increases everywhere inside that closed system. So a small amount of force exerted on a small area will translate to a large amount of force exerted over a larger area. And again, what you have on the screen right now is a very common problem that uses this technique. All right, I think I'll end it here. Have a good day. This is Mr. M, signing off.